Welcome, Mosè.
Thank you. Thanks for the introduction. Everything, so I don't need to repeat this slide. So what this talk will not be. So this will not be a, can you see, sorry? Can you see, okay. This will not be an introduction to Julia. Sorry for this. But Valentin Choravi last year or a couple of years ago gave already a talk in this series. So you can go and catch up the recording of his video if you want to know more about Julia. This will be more a overview of the tools available in the Julia language to do high performance computing. Also, this is a Pluto notebook. It's a notebook, it's interactive, but I'm running this on 6 different machines at the same time, the same notebook. So I will switch between the different, you can see here I have all the tabs. I will switch between the different machines at some point to show that the same code is working on different machines. But also this is a live demo, like this entire presentation is a live demo. So if something doesn't work, please be patient. And also you will see a tiring collection of methods to compute pi. So you will get bored at some point of seeing always computing pi, but you will be warned. So let's start with computing pi. So the first, let's say the easiest way to do parallel computing is to use shared memory parallelism, and Julia offers this capability. To showcase this, I will start by talking about this formula to compute pi, Bailey-Bowen-Plouffe formula. There are tons of ways to compute pi. This one is interesting because it gives you the nth fractional hexadecimal digit of pi without computing all the others. So you can say, oh, I want to know the 1000th hexadecimal digit of pi, and you can just get that one. And that's pretty cool. So this is the formula to compute pi, and then if you just want the digits, this is what you need to compute. There is a Wikipedia article about this. I'm not gonna do the proof of why this works, but you can read the Wikipedia article. Here I'm implementing in Julia the function. So just to give a taste of what Julia code looks like, you can define one-line functions like this, which kind of looks like mathematics, which is also something that Julia users are very proud of, like being able to write code which looks like mathematics. And then if you want a longer function, because it just requires more lines, you can also use the syntax function, then the name of the function, and also notice here that we can use Unicode characters for defining functions, as variables and function names, and then the arguments, and then the body of the function. So this just implemented this formula. I'm not going into the details. You can look them up on Wikipedia, but I'm just implementing the formula. And then I'm asking, like I'm defining this function, which gives me the nth fractional digit of pi. And then I concatenate all the digits. So I convert, I think, each digit to hexadecimal, like the string representation in hexadecimal of each digit, and then I concatenate all of them between, in this case, 1 and n. So when I call this function by string, if I can scroll down, yeah. If I call this function by string and they ask, and I pass the argument 13, I'm asking for the first 13 hexadecimal digit of pi. So this is what you get. And we can check that this works. So we can parse this string in hexadecimal as a floating point number in double precision, and we can check that this is exactly the same as the floating point, representation of the number pi. So this pi in Julia is a constant, is a variable which is already predefined. So we can convert it to floating to the double precision floating point number to see the value, and we compare with what we got from the hexadecimal expansion, and we get a true. So this works. So now let's not stop to 13 digits. We computed the first 1000 digits. So I can use big float is a built-in type in Julia to do arbitrary precision floating point numbers. So here I'm setting the precision to 4000, I think, yeah. And then I'm computing this bystring with 1,000 elements and converting, and I get again a true because this is equivalent to pi. So all good. And we can compute these serially. Fine. But again, all of this was because this algorithm gives you the nth decimal digit, hexadecimal digit, and so you can parallelize this work, which is cool. But there is one problem. These algorithms, like the computing the nth digit as a computational cost of n log n, which means this is very unbalanced. So the very first digit will be very quick to compute. The 1,000th will be quite expensive. So to do this, you need a kind of good scheduler to do the parallelism, because if it does like some silly static scheduling of the threading, they will not be very efficient. So let's see how this works in Julia. So first of all, it's always important, this besides Julia, but like an important point when you do shared memory parallelism, pin the threads, so that you know this thread is running on this core, it doesn't move, and like the operating system is not moving it around. In Julia, there is this package by Carsten Bauer called threadpinning.jl, which lets you interface with the operating system utilities to thread the pin, and also gives you some nice visualization here of the cores available and where the Julia threads are pinned to, and if there is hyper-threading or their efficiency core, these are highlighted here. So then this is a nice tool which helps with dealing with the shared memory parallelism. So I'm doing the pinning of the threads for good. Now I define I'm using a package called omithreads, which is a nice user-friendly way to interact with multi-threading in Julia. So you could also use, like, you could define the same function using the built-in functionalities in based on the threads. They work. I mean, omithreads is based on this one, but these are like the built-in blocks. It's not as user-friendly as using omithreads. So I recommend using omithreads if you want to do only shared memory parallelism on CPU. The only thing that I'm doing here is calling in a threaded for loop, well, in a task-based parallelism, the function PyDigit that we defined before, and then concatenating, like accumulating all the results after we run the task-based parallelism. So I run this. First of all, we check that the result is good. This is an assertion. Will get an error if this was not giving me the same result between the serial. This is the serial, and this is the parallel version. So no error, all good. Around this, sorry, this is another package in Julia to benchmark functions, which is quite nice because you can do this in the terminal very quickly, and in the Julia repo to get a quick overview of how fast your code is. So I run this, I compute the parallel efficiency on my laptop, I get 8%. Consider that this is not a great laptop. I'm running a Zoom call at the same time. The system is busy. I have a browser running lots of tabs. So let's check out another tab. Like this one, maybe. Let's see. So I just scroll. Yeah, I'm pinning the threads. I have 80 threads. It's quite a bit. Maybe this will not be as efficient as I hope. Yeah, I get 3%. That's worse. But so the problem when I have this many threads and the CPU is very fast is that 1,000 the first 1,000 digits are actually kind of quick, but that was not the problem. The problem was that the multi-threaded version didn't run as fast as it could. So now I'm getting 86%, which is much better. But I think if I increase the NPy to here, like 2,000, I should get a slightly better parallel efficiency. So parallel efficiency is computed here by getting the time to run the parallel version over the time to run the serial version. No, the opposite, sorry. The serial version over the parallel version divided by the number of threads is like simple. So now this is taking a while because it's running again the benchmark for the serial version, the parallel version, and all the things in between. While I wait here, this Pluto notebook is quite nice because it's reactive. So if I change a cell up here, doesn't scroll. Yeah. If I change a cell here that defines npi, it's automatically reevaluating all the cells below, well, anywhere that depend on npi. So unlike Jupyter, this allows you to have to not have a hidden global state. So I change one. It's kind of like a spreadsheet where you change one cell and then all the other depending cells change automatically. I don't know what is this low the first time. So yeah, well, this is why when I changed one cell, it was redoing lots of work. Yeah. But this should, yeah, 95%. This is much better. Right, so multi-threading shared memory parallelism is the easiest way to do some parallel computing also on your laptop, maybe not doing doing a Zoom call. And then the next one is doing distributed computing with MPI. So MPI is the de facto standard for doing large-scale parallel computing. And Julia has an interface to this. It's a package called mpi.jl. This, again, just interfacing the MPI library that you have on your system. So here I'm setting, so I'm using the package MPI. I'm defining the number of parallel processes that I will use for the following examples. I'm just capping to the number of actually available CPU threads in case they are less than 4. And then let's do some examples. So these examples are based by some lecture notes by Valentin Churavi about research software engineering, and he has a lecture about distributed computing with Pi. So I'm just copying these examples. Right, so this is sending some data around the ring. So you have 4 processes, and they are just sending each of them some data, one token, which is this number 52. They're sending it to the next rank in the MPI process. And then we can see, we can collect it's a bit slow. You can see here, this is a collected result of the operation of the sending the data around. We get 42 everywhere, so all the ranks got the same number. That's good. So one thing is, if you're already familiar with MPI, that's great, because MPI.jl just follows the same API as MPI. It's actually slightly simpler. For example, I think in the receive function or the send function in the full MPI API, you need to specify also the number of elements that you want to send around, the type of the elements. Instead here, we're using some Julia objects, so the Julia function send and receive can automatically infer the data type and the number of elements that you're sending around, so you don't have to do these things manually. So again, if you're familiar with MPI, this should feel very familiar. Actually, it's slightly simpler. If you're not familiar with MPI, maybe this is a nice way to get into MPI, because again, it's slightly simpler than the full standard C API. Another example, again, Pi, computing Pi, using 4 MPI processes again. So what we're doing here is to compute this integral. Is the integral between 0 and 1 of 4 over 1 plus x squared. This gives you Pi. What we're doing here is to take some slices and then let the each rank, and then we take, I think, 1 million slices of this range between 0 and 1, and we distribute across the 4 ranks that we are using for this MPI program. So all of them will compute one part of this integral. So what we get here in this output is basically the total of the integral that they computed, each of them, and then you do the sum, like you do the reduction, the sum of all the elements to get Pi. So if you sum these 4 numbers, you get Pi with an approximation of order of 10 to the minus 13. So this is pretty good. So does MPI with Julia works, or rather Julia with MPI work? So we had a paper 4 years ago now, I think, with Valentin Churavi again and Milan Klawa. So we did some performance analysis of Julia on Fugaku, which at the time was the system number 1 in the top 500 list. And among the things that we studied was computing, estimating the latency of MPI communication on this world-class system. So this was quite nice because RIKEN, the institute which runs Fugaku, provides some benchmarks already of the latency of the MPI operations. So we were doing the same operations using the Julia interface to MPI, using the system MPI library. And so you can see here that apart from the smaller messages, there was pretty good agreement for the latency between the Julia interface and what the RIKEN Institute found using the RC program. And if you compute the throughput, these are basically the same. So ping pong is sending a packet of data to the other rank, and the other rank receives it and sends it back. So it's just sending some data around between 2 ranks on 2 different nodes. So here we computed the latency. The first plot was the latency. The second one is the throughput. So how much data you send over the time. And first of all, you can see that if you want high throughput, anyway, you want to go to large message sizes. So anyway, you're kind of more interested in this part. And you can see that also for the throughput, there is pretty good agreement between what we found with the Julia interface to MPI and the just doing a C program. I think here the larger size, the difference was less than 1% of the throughput. So that's pretty efficient. Other operations, latency of MPI or reduced on 384 nodes using 1500 ranks. Again, there is some extra latency for smaller messages, but then for larger messages, the agreement of the performance is pretty good. The same for GatherV. So these are all standard MPI operations that we benchmarked compared to the what RIKEN provided. The usual refrain that we found a small overhead for smaller messages, but then this goes away when you go to larger messages. This was the more interesting one. So this, again, latency, so you expect lower time, better latency. I believe here what happened is 64 kilobytes is the L1 cache of the A64FX CPU. So I think here we were just hitting some cache. And like we were not avoiding the cache effectively. Instead, I know that the benchmark program that RIKEN uses, they do cache avoidance. So I think there is an artifact here that we are actually not doing any work in the reduction operation. But so yeah, this is not good, but again, for larger messages, we find again some the good agreement between the performance of the Julia API interface and the standard C programming. Right, wait a second, I forgot to press this button. Right. So far so good. Any questions? Pressing questions? Yes, some questions.
Do you know what's special about 16 kilobytes?
Yeah, so this is the. Yeah, so I think, I mean, this is my hypothesis, but 64 kilobytes is exactly the L1 cache of the CPU. So this is.
The earlier ones you had from 16 kilobytes onwards, it was identical.
I think here it's just disappearing the overhead. So there is a small overhead that then becomes negligible when you have larger messages. But here there is really a cutoff. Like the difference here is much.
Do you know what the overhead is? Different allocations and that sort of thing?
So overhead could be, so Julia, first of all, is it has runtime, it has a garbage collector, it has a compiler, it does some extra stuff which could add some overhead if you're not careful enough. But again, we found that this overhead is visible only for the smaller messages and then just disappears because you're doing more work than the overhead that is underneath. Any questions? No. So GPU programming. So again, we are going from the simplest way to do parallel computing to the more complicated ones. So GPU programming is, GPU nowadays is everyone's favorite accelerator. We can use it from Julia. Last week, I was at a conference together with Valentin again, where he gave a talk about the Julia GPU ecosystem. So this is available on his website. I don't think there is any recording, but you can find the notebook that he gave if you go to his website. I will actually follow here a couple of things that he shared in his talk. So first of all, a guiding principle in the Julia GPU ecosystem is that the compute follows the data. And in particular, we use data wrappers, so like some type wrappers around data to identify where the data lives. So you have a data type called QArray, which is a data type which represents data which lives on a CUDA GPU. You have, I think it's called the ROCm array for data which lives on the AMD GPU, and so on. Like for all these array types, you have some wrappers. And this is very important because this enables us to say, oh, this data lives here, so I will do some operations in a specific way because I know that the data is on the GPU, on an NVIDIA GPU, so I will do things specifically for an NVIDIA GPU, or no, I will do something specifically for a Intel GPU if you have an Intel GPU and so on. This can be problematic nowadays when you have unified virtual memory between CPU and GPU, because maybe you allocate memory on the CPU and then it's magically available on the GPU. So at the moment, the model is always follow the like create a wrapper for where the data lives. Unified virtual memory is a bit of a question mark. I mean, you can actually create a like in CUDA, the CUDA.jl package as a way to create a CUDA array, which actually lives on also on the CPU. But still you need to convert it, dereference it somewhere manually to say, oh, I'm now accessing this data that was initially allocated on the CPU. Right. The other thing is in the Julia ecosystem for the GPU specifically, there are different levels of abstraction. So if you want to do things kind of low level, you can use the packages that more closely are like closer to the vendor-specific toolkits. So, for example, for the NVIDIA GPUs, there is a package called the CUDA.jl. For AMD GPUs, there is a package called AMD GPU. For Intel, there is OneAPI.jl, and for the Apple GPUs, there is a package called Metal.jl. So this, if you want to do things very vendor-specific, which you can do, but maybe this is not very portable, right? So for this, there are some abstractions, and one of them is called KernelAbstractions, again by Valentin. KernelAbstractions is actually interesting because it works not just on the GPUs, but also on the CPU. So you can write this code, and this will work on both your CPU and on the GPUs. The only thing that you need to change is this argument, basically, the backend that you're passing. But then the function that you defined is the same everywhere. One thing which is probably already visible from here is that KernelAbstractions forces you to write a kernel in a GPU-like way. This is important because when you write code for GPU, you're already implicitly forcing a parallel style. So it makes it easier to do some optimizations, and like the parallelism is already kind of explicit by the way of defining a kernel for a GPU. But also in Julia, there are other array abstractions that you can use. So if your Y and X here are again Q array, like the arrays that you live on a CUDA GPU or any other GPU families that I mentioned before, you can also just do these operations using the standard Julia function. Like here, it's not even visible that you are calling the CUDA functions or the AMD or the Intel or the Apple Metal functionalities, because this will be automatically dispatched again, because the compute follows the data. This will be automatically dispatched to the underlying functions that will do the operation, in this case, the plus AXPY operation for you. Right. So to be a little bit more concrete. Yeah, so what I do here, oh no, this is not my laptop. I need to find my laptop. Yes, okay. So what I do here is to load the kernel abstractions and then all the vendor packages that I mentioned. So CUDA, OneAPI, AMD GPU, and Metal. You will get some kind of scary warnings if you try to load a package that's not supported on, like the GPU is not supported. But actually, this is non-fatal. It's just a message just telling you, oh, this will not work. But again, it's not fatal, so I can load the package and just don't use it, and that's it. Right. So here I'm defining, again, a kernel to compute pi. This is using the same method as before of computing the integral of 4/1 plus x squared. So this is the kernel defined using kernel abstractions. Again, you can see that we are accessing the global index and using it for defining the rank of the kernel. Sorry, for the rank, we use it for storing the results into this results vector. And then this is a function which is simply calling this PyKernel above. So it's calling it here. And in addition, this is allocating the array where we will do the compute, calling it, synchronizing it, and then doing the reduction. So accumulating all the results to do the sum and get hopefully pi. This is yet another function, but just to print the results and doing the benchmarking. So before calling this function, I will get the time. Or get the time before and after, so that I can do some benchmarking, right, and print the values. So okay, so I do this on CPU using the floating point number float32 is a single precision. I specify the number of steps to compute this, and this takes 0.044 seconds. But now I want to see, does this work on GPU? The same code. I'm only switching the backend. On this laptop, I have both a NVIDIA and an Intel GPU. So I can use on this laptop 3 different kernels in KernelAbstractions, which is kind of nice for this demo. So this is not what I wanted. Live demo, yeah. I suspect I will have to restart this on the book here. Let's see if at least the OneAPI works. Yeah, okay, so I think this is working, yes. So remember, this was, I think, taking 0.044 seconds on a CPU. And on the GPU is a bit faster, on the Intel GPU. And actually, if I enable this cell, it should be. Okay, this is becoming not very responsive. Yes. Okay, doing this with a Zoom call at the same time is a bit challenging. So yeah. So you can see that the GPU, this one is a GPU and this is the CPU version. So you can see that this is a bit faster, which is good, what you expect from something called accelerator. But let's go to the meta GPU. So here I'm switching to a tab where I'm accessing the same notebook on a MacBook, Mac Studio, Mac Studio. This is very slow. Sorry, my browser is under stress. Okay, fine. Right, so again, I'm using the same notebook, but here I have only the CPU and the metal backend. One interesting thing of the metal backend is that the metal GPU only supports single precision. Like you cannot do double precision floating point numbers at all. So now I'm computing this by on the metal GPU. I'm doing some warming up because I didn't mention, but Julia is just-in-time compiled. So the first time that you run the code will take some time to do the compilation stuff. But then hopefully later times are a lot faster. Yeah. So what I wanted to show, if I can use my browser, is right, I mentioned that, yeah, the floating point number on the GPU, metal GPU, is only a single precision floating point numbers, or well, also a half precision, I think, but we don't have higher precision than a single. But in Julia, there is a package called multifloat. Wait, where is it? Here. Multifloat, which was developed as part of a PhD thesis of a guy. He basically implemented the arithmetic of like the basic arithmetic operations. You basically can represent a double precision floating point number using two single precision floating point numbers. And this is great because then you can do double precision on a metal GPU. But also I want to stress that this is a custom data type. So I'm able to use a custom data type that someone prepared, and I get the result. And in double precision, the relative error is pretty good. And now the most challenging part will be to click here. Enable again. So what I want to try here and see whether, so in this second cell, I'm running always on the CPU. The first one is on the selected backend that was the metal GPU. But what I want to see, okay, yes, yeah, kind of. So the metal GPU using this double precision, using the two single precision floating point numbers, is actually still slightly faster than the native double precision on the CPU. So again, this is kind of interesting because you can actually do double precision on a GPU that doesn't support it natively, and still be slightly faster than doing the operations on a CPU. And this also is kind of important in modern day compute, where all the GPUs are getting smaller for different numbers. So yeah, having these tools available is very important, and this looks to work and have good performance. And also to show you, does this work also on AMD GPU? I'm now switching to an MI300X instance. I also need to show NVIDIA because it failed on my laptop. So yes, so this is AMD GPU. So I select here the ROC backend. So this works, and it's quite fast actually, because it's a very high-end GPU. Yeah, this is a lot faster than the previous GPU, as you can tell. And I can also do again the trick of using the other backend, sorry, the other floating point number. And also here there is 2 single precision to do a double precision, or 4 single precision to do a quadruple precision, and even this is again quadruple, this is octuple, I don't know what it's called. But yeah, on the AMD GPU, you can also use the double precision natively, the double precision floating point numbers. And again, the custom data type. And this all works, and this. But first I want to compare again with the CPU version. No, this is a mistake. Oh, okay. Let's see if I can type. Before. Yeah, you can see that the two single precision floating point numbers on the AMD GPU are quite a lot faster than doing the same computation on the CPU in the native double precision using 96 threads. So yeah, this GPU is pretty good, and this works. It's great. And now let's find another NVIDIA GPU that I can actually use and doesn't crash. Yeah, so this is the CUDA GPU. It's like sorry, the browser is very slow. But yeah, I hope that I convince you that this works on all the different backends. Don't do this during a Zoom call, apparently. Right. So other tools that are useful when doing high performance computing, like you want to do, like you want to understand why your code works or doesn't work or is not doing what you want. So I don't know if you know the website called the Compile Explorer, godbolt.com, something like that. So there you can basically paste your function and then get the native code, or if you use an LLVM-based compiler, get the LLVM intermediate representation and so on. In Julia, you can do all of these in your REPL very easily. It's simply, but this is very long. I need to scroll. So what I'm showing here is a called typed code in Julia. It's not too much. Spoiler. No. So this typed code is an intermediate representation before getting to the LLVM intermediate representation and then to the native code. but it's this I very like because it allows me to get further and further in the compiler pipeline and see what's happening in there. And so you have the different macros to inspect the generated code. This is the LLVMIR. So I don't want you to understand what these represent, but just to so that you know that you have all these tools that let you inspect the compiler process, the compiler pipeline, and see what's happening. And if you are familiar with the native code for a GPU or also the CPU, you can also inspect that one. So if you want to do very low-level performance engineering, you have all these tools. And yes, other tools are profilers. Don't go fast now. Other tools are profilers. Okay, sorry. Other tools are profilers. You can use, so Julia comes with a built-in profiler, but you can also use external profilers if you're familiar with them. I don't know, like Intel VTune, NVIDIA, both the system, it's called Insight systems and Insight compute. Or in general, if you look for profilers, make sure that they work with Java, because Java is also JIT compiled. So if it works for Java, there is a good chance that it will work out of the box also with Julia. Even if they don't say, oh, this works with Julia, just search for Java. And to show you that this works also with Insight Compute, which is a very advanced compiler, profiler for the NVIDIA GPUs. Here I was benchmarking. Maybe I can zoom in. Yes. Here I was benchmarking the this PyKernel. So I was benchmarking the PyKernel, and in particular, this one was the kernel I was most interested in. And I was getting a 90% of compute throughput, which is pretty okay. And some other metrics. And then other nice things that you can get are these. Okay, so this is a roofline model, but again, this is just automatically generated by the profiler. I wasn't doing anything special, just to show that all these tools also work with the Julia language. The other one was this one. Yes. So this is showing the register pressure in the program, and it's quite nice because you also get the Julia code, so you can look at the Julia code side by side with the PTX if you're familiar with looking at the PTX in this case. And so you can get also this very helpful debug information, which make inspecting your code easier and doing all the performance engineering work much easier. What else? Right, now we can go to, does this work again? Like the Julia GPU stuff. So first of all, people are happy. Katie is actually one of the most involved people in the Julia GPU ecosystem. But some years ago, she just ported some code from CPU-based C++ to Julia, GPU accelerated, and the speed up was very significant. So people are happy if they're able to use the tools very efficiently. Shenanigans is, I think some people here know it, is a Ocean model, which a few years ago, go down. Right. A few years ago demonstrated very high energy and memory efficiency compared to competitors. So that there is a paper on arXiv if you want to have a look. And this is entirely written in Julia using kernel abstractions. And so this is mainly tested on NVIDIA GPUs, but in principle, well, the people that are in Birmingham today, they can confirm whether this actually works also on AMD GPU. Again, the only thing is it's not extensively tested on the other GPUs, but there is the work there to make it work with other GPU families. Other packages that use kernel abstractions, or in general the Julia GPU ecosystem, are parallel stencil and implicit global grid.jl. These were developed by Ludovic Russ. This was a study done on a PISA Dint, the CSCS supercomputer. Well, these are very old now, 2019. But still, these have showed very good parallel efficiency on up to 5,000 GPUs, which I guess is a good result, and also comparison with a kind of CUDA C++ equivalent model. I don't want to claim that you always get better efficiency with Julia. This is just one case where it was good, but at least it can be very competitive and very efficient. And there are also other people happy, like Water Lily is another computational fluid dynamics model. People ported to GPU using kernel abstractions, so they were able automatically to use it on multiple GPU families, and they got super fast real-time visualization of the simulation. So yeah, you can see that people use these tools, are happy, and I guess this is hopefully a proof that this tool work. What else I have here? New development. So Qtile is a new package developed by NVIDIA for doing some kind of low-level programming of the new Blackwell GPUs. And for this, I will switch to my Blackwell GPU. Okay, so this is first of all, very specific to NVIDIA GPUs at the moment. Qtile is open source, so in principle, other vendors could adopt it in the future, but at the moment, this only works on NVIDIA GPUs, and specifically only the Blackwell generation or later. So this is an example taken from the documentation of Qtile. So Qtile.jl is the interface to this Qtile package by NVIDIA. This is very low level, so it's not maybe the nicest things to read that. But in practice, this is defining the kernels to do the matrix multiplication on the GPU. But the important thing is that this code, if you take it side by side with a Python equivalent, they look very similar. So this makes also porting the code from a Python version of the Qtile framework to Qtile.jl kind of easy. And then you can run it on the GPU using different matrix dimensions and different tiling. And yeah, it works. Again, the only constraint here is that this is in only specific CUDA NVIDIA GPUs. Before finishing, I want to mention that there will be the JuliaCon conference in Mainz in Germany, so not too far from here. You can even get by train if you trust German trains. It will be in August, from the 10th to the 15th of August. And if you're interested, you're more than welcome to join us. Unfortunately, the call for papers is closed. Yes, so that's really close. So in case you had some Julia work to present, you can come to learn about what people are doing in Julia. And with that, I think I will leave it. There are questions. I also have other things I could show, but I will leave for questions. Thank you.